Hi there, everybody. In this video, we're going to talk about how to solve rational inequalities, that is, inequalities involving rational functions. And here is an example of a rational inequality right here. Notice we have a rational function, that is a quotient of two polynomials. We have a polynomial in the numerator and a polynomial in the denominator, and we've made an inequality. So this is a rational inequality. This is going to be very similar to how we dealt with inequalities involving polynomials. Right? So if you are not familiar with that, go back and watch my video on polynomial inequalities and then come back and continue along with this video. But let's just refresh our memory on how that worked over here. Here is the graph of a polynomial. Now, if I wanted to know where this polynomial was positive, well, I'll be looking for where the graph is above the x-axis. This is where it's positive. If I wanted to know where it was negative, I'd be looking for where the graph was below the x-axis, over here. Now, polynomials are continuous functions. What that means is that the curve can be drawn without lifting the pen from the paper. I can draw the entire polynomial without ever lifting my pen off the paper. And what that means is that if a polynomial is ever going to change sign from being positive to negative, it has to pass through the x-axis in between. And so to identify where a polynomial is positive or negative, we look for where the polynomial equals 0. And that will be these points over here. And that splits our real number line into intervals, and then we explore what the polynomial is doing in those intervals just by plugging in numbers and checking. So the key is to set the polynomial equal to 0 and solve. And then from there we can solve the polynomial inequality. Well, let's take a look at a rational function. Now you'll notice that they can look quite a bit different than polynomials. And one major way in which they are different is that rational functions are not continuous. So if a rational function changes from negative, here we see it's below the x-axis, to positive, here we see it's above the x-axis, it does not need to pass through 0. It does not have that property that I can draw its graph without lifting my pen from the paper. I have to lift my pen off and put it back down, which means it's allowed to jump over the x-axis. So we just need to take this into consideration when we deal with rational inequalities. Not only do we need to look at where they are 0, that is where they could change from negative to positive, or vice versa, but we also need to look and see where this could happen. See what's happening here at -1. It went down to negative infinity, jumped back up to positive infinity, and then came down. It changed from negative to positive. Well, how can it change? How can it jump like this? Well, that's where it has an asymptote. If they have asymptotes where the denominator is equal to 0. So the idea is we're going to be looking at where the numerator is equal to 0 and where the denominator is equal to 0. Okay, so let's look at an example and work our way through it on how to solve this rational inequality. All right, so here's the example that we presented at the beginning of the video. So we want to solve this rational inequality. Now the first step, just like in polynomial inequalities, is you're going to want to arrange the problem so that you have a 0 on the right-hand side. If this is not a 0, then the next steps that we're going to do are not going to work. First thing you have to do is get this to be a 0. So you can use algebra to get that to happen, but you're going to need to get that. Here we already have it equal to 0, so we're fine. Okay, so then you're going to want to make sure that the expression on the left is a rational function, a polynomial divided by a polynomial. And again, you might need to use some algebra to get it into that form. The next step you're going to want to do is you're going to want to factor the numerator and denominator. So pause the video now, take a moment, factor the numerator and denominator. Okay, so let's check our work together. I'm noticing that in the numerator, I see a GCF, a greatest common factor, is x. So I can factor out the x. And in the denominator, I think we can factor by grouping. In the first two terms, I can see they have a common factor of x squared, so I'll factor that out. And in the second two terms, they have a common factor of -1, so I'll factor that out. Okay, so I've simplified, so I've factored the left-hand side to look like this. Now I can factor it some more, because this is x plus 2 squared, so I'll go ahead and write that in. And in the bottom, I see that x plus 2 is a common factor, so I'll factor that out. And what's left over is an x squared minus 1. Okay, I'm getting there. But I still can factor one more thing, and that's the x squared minus 1. X squared minus 1, that's a difference of squares. That factors as x plus 1, x minus 1. So let's go ahead and finish off this factoring. There we go. This is where we want to be. We've factored the numerator and we factored the denominator. So what we're going to look for now is where the rational function is 0. Right? So that's where the numerator is equal to 0. So set the numerator equal to 0 and solve. Well, where does that happen? Well, that happens when either of these two factors is 0. And that's going to happen when x equals 0 or when x equals -2. Okay, next we're going to see where this rational function is undefined. That occurs when the denominator is equal to 0. So now we're going to set the denominator equal to 0. And we're going to solve for x. And that's going to happen when any one of these factors is equal to 0. So I can see that happens at x equals -2, -1, or 1. So I'm going to look at all of these numbers. These are going to split the number line into intervals. We have the least number is -2, so let me mark that. We have -1, we have 0, and we have 1. So these are where the rational function can change sign. Now, does it necessarily change sign moving from one to the other? Well, no, that is not the case. So we need to check each one of these intervals individually to see what the sign is going to be. So let's take the interval furthest to the left. So what we can do is we can just take a number in here, like -3, and just plug it into the function. And you can compute it and just see, do I get a positive number or a negative number? But you could also be a little bit less specific about things and just think about what's going to happen. If I take -3 and plug it in here, what am I getting? I'm getting a negative number here, and this is going to be positive because it's squared. So the numerator is negative. The denominator, let's see what happens there. If I take -3 in here, this will be negative, this will be negative, and this will be negative. Negative times negative times negative is negative. So in total, I have a negative number divided by a negative number, so the result will be positive. I don't need to compute exactly what the answer is to know that it's positive, although you could do it that way if you wanted. Now, what about in this interval between -2 and -1? Well, this is negative, and this will be positive, so the numerator is negative. What about the denominator? Well, if I'm greater than -2, this term is positive, but I'm in this interval, so I'm less than -1, so this one is negative, and this one's negative. Positive times negative times negative. Well, that's a positive. So I have a negative divided by a positive. That means we're negative. Now, what happens in this interval between -1 and 0? Well, this is negative, this is positive, numerator is negative. What about here? This is positive. I'm greater than -1, so this is positive, and this is negative. So I have positive times negative. The denominator is negative. Numerator is negative, denominator is negative, so the result is positive. Now I check this interval between 0 and 1. This is positive, numerator is positive. A number between 0 and 1 plus 2 will be positive. That number plus 1 will be positive. If I subtract 1, it'll be negative though. So I have positive times negative, the denominator is negative. So I have a positive number divided by a negative number, the result is negative. Now finally to the right of 1. Well, this is positive, so the numerator is positive. If I'm greater than 1, all of these are positive. Positive times positive is positive. So positive divided by positive is positive, so there we go. So in this case, we did alternate, plus, minus, plus, minus. Don't think that it'll always work that way. You do need to check. There are lots of examples where it will not alternate, so we do have to be careful. Now, what are we looking for? We're looking for where it's positive. So that's these intervals here. So my answer is going to be this interval, which is negative infinity to negative 2, union negative 1 to 0, union 1 to infinity. That is the answer in interval form. Now, it just so happens that the rational function that I had graphed and was showing you earlier is the graph of this function. So let's just take a look at it and verify that what we have written there is indeed correct. You can see that it is positive. It's above the x-axis from negative infinity up to negative 2. It is above the x-axis from negative 1 to 0. And it is above the x-axis from 1 to infinity. So the picture confirms what we had written down as our answer. Okay, so just one more thing to discuss here, and that is, what do we do if the inequality is greater than or equal to 0 instead of greater than 0? Well, we would proceed with the problem the same way. This would be greater than or equal to 0. This would be greater than or equal to 0. We would go through all the same steps in solving the problem, except when we get to this point, we have to do one more investigation. We need to investigate the boundaries of these intervals. Should all these intervals really be open intervals, or should some of them include the boundaries? In other words, should we use square brackets here? Well, let's go look at the picture and see what happened. Well, in the picture, you can see that where the function is greater than or equal to 0 goes, it's greater than or equal to 0 up to negative 2, but not including negative 2 because it's not defined there. So that means we leave this interval open. We use a round parenthesis, so that is correct. Now what about near negative 1? Well, near negative 1, we see that the function is not defined at negative 1, so it doesn't make sense to say that it's greater than or equal to 0 here, or to say anything about that function there. So we have to leave it open. We can't talk about its value at negative 1, so we leave this open. What about at 0? Well, at 0, if we look at the picture, here the function is equal to 0. And 0 is greater than or equal to 0. And so this is included. So that is one adjustment that we need to make. We need to make this a square bracket here to indicate that 0 is part of the solution. What about this number over here, the 1? If I look at the picture, the function's not defined at 1, and so it doesn't make sense to say it's greater than or equal to 0. So again, we leave the interval open. And so this is what the answer would look like for the inequality greater than or equal to 0. We would have it all the same except we put a square bracket here. Now, we appealed to the picture to make to draw these conclusions. How could you tell the answers just by looking at the expression? What if you didn't have the graph on hand? Well, you can still do it. It's fine. You just have to plug in these numbers and check. So just take negative 2, plug it in here. What do you get? Does this become a true statement or not? Well, you'll see if I plug negative 2 into this expression, the denominator becomes 0. Notice this term right here, this factor becomes 0, and so that means the whole thing is undefined, so that means it's not greater than or equal to 0, so that means we don't include the negative 2. What about the negative 1? Same thing, makes the denominator 0, so the whole thing is undefined, so this is not a true statement, so I don't include the negative 1. I leave a round bracket. What about 0? Well, if I plug in 0, the whole thing becomes equal to 0 because the numerator is 0. It's not undefined, it's perfectly defined, it's equal to 0. And that is a true statement. 0 is greater than or equal to 0, so I include the 0. And what about 1? Well, 1 makes the denominator 0. It's undefined, so it is not part of the solution. So we leave an open bracket here, round parentheses. So that's a way to do it just by looking at the function. Now, I just want to point out that you have to be careful to do this before you've canceled any common factors. If you cancel common factors, you may hide the fact that the function's not defined at -2. If we were to cancel these, now you wouldn't see that. So make sure you look at the unsimplified form, the uncanceled form, when you go and make these investigations at the boundaries of these intervals. So this is how we would handle the problem if it was greater than or equal to.